National University of Singapore. He's gonna talk about he's gonna talk about is that the okay again cross-domain recommendation while clustering and multi-layer graphs. So let's look at different techniques.
Yeah, more interesting, the fourth speaker also from National University of Singapore, but this one you'll know later. So anyway, so I'm Alex from NUS, as you say, and I'm going to talk about cross-domain recommendation via clustering multi-level graphs. And basically, the name of this paper is agenda as well, because we will be doing recommending in one domain based on data from other domains, and we will be utilizing the group knowledge, which is obtained by clustering on the multi-layer graphs, and these multi-layer graphs represent the cross-domain interactions of the user. It's a joint work between ITMO University in Russia and National University of Singapore. So basically, what is venue category recommendation? Our main domain is venue category. So what is it? It's recommending of some venue categories, such as shop, such as maybe ice cream shop or some cinema, based on the same source, same domain data, which is same categories, in a simple collaborative filtering manner. So we use our friends' data to basically recommend our feature. And there is idea actually saying that if we utilize group knowledge together with individual knowledge, actually it could improve recommendation. So we employ this idea, and our recommendation part is very simple, but it consists of two parts. First is the history of some user community, some group of people that are related to us, and places where they go, and our personal history and past. So it's nothing too interesting here. That's how we recommend. And why we believe that user communities are important. No, first of all, we think that those people who are in the same community with us, they share similar interests with us. So we hypothesize that in theory they could visit similar venue types in future. And another computational issue that if we just recommend within one community, then we can significantly reduce the search space. So we don't need to go through all users. We only need to go through users inside one community. User community can be some distinctive group of people relating them in a certain principle. And in our case, we treat communities as interest communities. We hope to get interest communities as a result. And how to represent users? Well, conventionally, we represent them as some graph. And our edges are relationships, and our vertices are users. This graph can be built in many ways. In our case, we build on user-generated content, so some representations of data, some features. We measure the distance. For example, cosine distance. In our case, we use heat distance. So that will be our edges. And communities in such graph is basically 10 subgraphs. And one of way to formulate communities is a so-called min-cut problem, which can be successfully approximated via solving the standard trace minimization problem, which is by Euler theorem can be solved by eigendecomposition of the Laplacian matrix L here. So and further clustered by some k-means clustering, for example. There is another idea that I want to highlight is the utilization of multi-source data. Why we talk about this? Because it's known that even by web index search in 2016, it's more about 3 people using continuously, actively using multiple social networks, in particular 3 networks at the same time, and they're registered in 6 networks. So it's very reasonable to utilize such multi-source data so that we will see a 360 view of the user rather than just utilizing some one modality we pick up by chance. So in our case, we will be utilizing Foursquare, Twitter, and Instagram data. So now our task will become different, right? Based on multiple data sources from 3 social networks, this data is will be multi-source and multimodal, such as images from Instagram, text from Twitter, and locations from Foursquare. We want to recommend in our tagged source, the venue category source in Foursquare. And of course, since we want to do this kind of recommendation based on multi-source data, the community detection approach must be also based on multi-source data, otherwise we cannot utilize this data. And this basically is the main problems, main issues we face and we try to solve in this paper. So our main problems are data source integration, because we have multiple data sources, and community detection based on these multiple data sources. So how to treat it? Well, there's one way. We can represent our data as a so-called multi-layer graph, where our vertices are still our users, and edges are their representations in different social networks. For example, red one can be Foursquare, blue one can be Twitter, and green one can be Instagram. So there's also formulation of a spectral clustering for this case, where we just sum up Laplacians and compute eigen decomposition of the target sum of the Laplacians. But this one was found to be suffer from the generalization problem. So actually, it's a good way to regularize the formulation so that we will consider layers when we learn final target representation. And to regularize it, we actually need to measure the distance between different layers, different subspaces, which can be done by utilizing the Grassmann manifolds, so that you can get a value between two subspaces. And this value can be used for regularization further. And this regularization can be performed in this way. We actually can have our standard trace minimization problem as well as this regularizer that basically says our target representation U must be learned in a way it will be close to all other layers. So it literally will be latent representation. We can rearrange this term, so we'll get a new Laplacian called L mod. And then further we can just do a decomposition of this Laplacian and get the final representation. However, there is one issue here. As I said, all our layers, when we will be computing the target Latin representation, will be equally similar, equally treated when you are computing that. So, which is unfair in a real-world setting, because you may behave one way in one social network and completely different in other states. So we need to consider this relationship. So this gives birth to our fourth idea of making sense of interlayer relationships. So how we do that? Well, we perform this kind of regularized clustering one more time for each layer. And we do it in such a way so that we will consider the relationship between our learned layer and all the rest layers. So literally, if we have some relationship coefficient for Twitter, we will make the space for the Twitter learned in a way it will consider both Instagram and whatever number other social networks. So they will be consistent for each of them. And then we will be just performing the previous steps so that you'll get final Latin representation in such a way. And this is good, except for one problem. We don't know W. So we propose some empirical way to compute this W. What we do here, we perform clustering in different social networks, just for one social network, for different K, for different number of clusters. And then we measure how much these social networks are similar to each other in terms of spectral clustering. And then we average over all K, so we can get some measure that somehow tells us how much similar these two social networks to each other in terms of clustering, so that we can put this W inside the formulation and get the final Laplacian representation. That's how we detect our multi-source clusters. And this is final representation. Here you can see one more Laplacian, the final Laplacian, which obtained after some simpler arrangement of the above formulation. And we can again compute again decomposition of this Laplacian and then apply, for example, k-means to get the final clusters. So this is how we perform our clustering in this work. And basically we solved two of our main problems because we now know how to perform clustering multi-source data. So we just recall, we use multi-source data and some personalized history from Foursquare to predict Foursquare categories, to recommend Foursquare categories in future. And we can do our experiments. Another issue for this kind of works is actually data set, because many data sets, as you noticed last time, they don't have explicit mapping between different social networks. Luckily, for this work, we have a data set. It's the largest so far data set, multi-source, multi-learning data. It's called NUSMSS. It was contributed 2 years ago in ICMR conference. So that we have explicit ID mapping between different social networks, and we can build the joint matrices of different social networks. This can be also downloaded from my website, justmyfamilyname.com later if you want. And this data set is presented in terms of 3 feature types. First is Twitter features, which is mainly text and is LIWC and LDA features. Another one is Foursquare features, which is mobility tracks, as well as distribution among venue categories, as well as the image features, which is basically distribution of image concepts by applying image network trained, Google network trained image dataset. So this is our baseline. Do I have some time? I can explain. Yeah. So basically, baselines are split into two categories. First category is the conventional recommender systems. Some of them are very simple ones, some of them are more sophisticated, like factorization machines or SVD++. In the right side, we also can see the different clustering approaches, as well as our modifications of our approach, because we not just regularize it 2 times, we try all other modifications without one regularization or totally not regularized, which is just some of my classings. So we want to cover all the potential cases, how clustering can affect our results, as well as how other recommender system can compete with our recommendation. And first of all, we will compare with the recommender approaches. What is interesting to see here is that, for example, such models, such strong models as SVD++, actually perform very poor in most of the times. And we think this is related to the fact that venue recommendation domain is a little bit different from other recommendation domains. For example, if you didn't visit some certain category of location, it doesn't mean you don't like it. So SVD++ somehow cannot utilize this implicit feedback, or maybe utilize it strongly, so take something as granted, which actually doesn't exist, relationship that doesn't exist inside data. Another reason can be that Foursquare users just don't want to reveal some types of places where they want to go, but they still like to go to places. So this is this bias always exists in social media research. Another interesting observation here is that in one city in New York, the very simple baseline, popularity baseline, actually outperform all other approaches, including our approach. Well, it's only in 1 out of 6 cases, but it happened, and we studied deeper. What's the reason? The reason was that in New York, people use Foursquare far more than in other cities, so that the location, the venue category data dominate there. And just your previous history of visits can actually cover your future. Because we need to know that location domain is a very specific domain. We may revisit some items that we visited in past and future, as compared to, for example, e-commerce, when we maybe not buy often things that we already bought in our past. So this could be a reason. And well, of course, our model performed quite well in other cities, in other taxes. We always black box line. Here, we compare with other community approaches as well as modification of our approach. All secure bar is a modification of our approach, and we also compare with X-means, with dbScan, and with hierarchical clustering. So here, what we can find is that first, it's important to incorporate group knowledge into recommendation. So all the clustering approaches perform decently well compared to the original performance. Then we can notice that multimodal clustering perform better. In fact, the regularized multimodal clustering perform better than non-regularized non-regularized versions, as well as single model Foursquare clustering. This is fine, it's encouraging because it somehow supports our initial assumptions behind this study. We then later also see the contribution of different data sources, and here we found some more or less straightforward results. For example, the data from a target domain, from recommendation domain, such as location data, is the most powerful contributor towards the recommendation. However, you can see that even if you don't utilize just location data, you may utilize other data sources, we can still get some nice recommendation results, which actually refers back to your question again. Yeah, we can use images to recommend locations without knowing locations. It really works. It's probably related to the user interest, and user interest somehow correlated with the places we go, which, well, can ask social scientists to study that further as well. So
you have examples. You have examples show you have images for recommend
I have examples of 3 user communities here, which basically show, okay, well, these names are given by myself by looking at top words inside this user communities, this user post. But of course it's not words, this one is really words, it's text. This one is a visual concepts, like mouse, digital clock, hard disk. This is locations, like electronic store, startup, technology building as well. So our algorithm, our clustering approach actually detected people in one community, and these people do text about devices, do take pictures of watches, hard disks and mouses, and at the same time they do go to electronic stores. So their activity in different social networks of a different modality somehow very correlated to each other, and it's very exciting because it means this kind of works can be continued and we can further study that. And there's two more examples. Actually, we can read it from a paper. There's much more interesting stuff inside. Unfortunately, I can't include in slides due to the time issues. And our future works are based on the assumption, well, community detection is good, but it must be domain specific. Because sometimes we may detect communities related to travel, for example, but we want to recommend, I don't know, devices to buy in a camera store, which doesn't make my sense. So how we plan to do that? Yeah, we will be either embedded inside the graph itself, so we can adjust the graph weights, or another way we can actually constrain the spectral clustering. There is a reformulation of spectral clustering called generalized spectral clustering. We can put constraints which user will be putting in one community explicitly, which for sure wouldn't be in one community. So we have some ground truth on this, like user communities from Facebook, for example. Then we can actually tune our clustering so that results potentially will be improved, at least in certain domains. Yeah, multi-view data is crucial for our tasks, and both group knowledge, individual knowledge are important. Finally, our task value category recommendation is not that similar to other recommendation approaches, because many items from past will occur in the future. So that was found from the popular baseline strengths. That's basically all. Some people asked me during the conference about the datasets. We actually released 2 multi-source datasets. And one dataset includes data from multiple social networks, from Instagram, Twitter, and Foursquare, while another one very recent from AAA this year. It includes sensor data, real sensor measurements of people who are going for workouts. So it's very exciting research can be done. We currently working on both datasets. First one can be used for research on cross-country and cross-distance research, while second one can be used for different wellness and e-health related domains. So I would highly recommend check it out. And also for those who may be interested in this topic in general, I just gave a 3-hour tutorial in one of the Web Science Trust events. So you actually can go to this link and see the whole tutorial. I'll be describing all works related to this. And that's all. Thank you very much. Any questions?
Great. Any questions? By the way, do you have a source code available?
For this particular task, yeah, we do have available source codes. If you go to the my web page, which is here, parcel.com, you can actually get that. Or you can ask via email. I'm not sure. I'm updating the web page now, so I'm not sure is it link saved there or not. And then for the rest of the works, we have data and source code. This for some of them, yeah.
Any questions?
Yeah, I'm fine with any questions you can ask. You can ask something tricky, interesting. Always into discussion. We can discuss later if you're curious about the thing.
What's the weather this evening?
Well, the storm gonna not come. Yeah, because the Japanese government is very powerful, so they have to go.
Yeah, I heard there was a talk about earthquake this morning. Someone said. Well, we see.
Well, at least in my hotel, I sleep too well, so I didn't hear it.
Thumbs up. All right. Let's thank the speaker again. The last one is about advertising.